I'm Ramon Ricafort, faculty member of the School of Mining, Energy, and Manufacturing of Saskatchewan Polytechnic College, Musjo campus. Today, I'll be presenting a research project entitled Recycled PET as Composite Structural Material. This project supported by the Office of Applied Science, Research and Innovation of Sask Polytech. A study conducted by University of Toronto as little as 50% of water bottles are recycled, meaning the rest ends up in landfill. This translates up to 65% water bottles end up in landfills every year. Once in landfill, it will take 50 to 1,000 years to decompose. According to the most recent municipal solid waste report from the EPA, most of what is recovered consists of PET and HDPE plastics, as they clearly dominate the plastic recyclable market. So what we can do to help? Okay, to respond to the call of the government in reducing the generation and mismanaged disposal of plastic waste, thermoplastics, especially PET, will be recycled, presented by the primary recycling due to their simplicity and low cost. Instead of the traditional way of recycling plastics back to its original product, this project focuses on strengthening the mechanical properties by experimenting with an additive like calcium carbonate and stearic acid as fillers. This will be presented here to cover the first phase of the study. One thing good about the thermoplastics material is that it can be softened on heating and hardens when cooled, since these are made up of linear molecular chains. Okay, mechanical recycling refers to the operations that aim to recover plastic waste via mechanical processes like grinding, washing, separating, drying, regranulating, and compounding, as shown on the right of your screen. For mechanical recycling, only thermoplastics materials of interest, like polymeric materials that may be remelted and reprocessed into different shapes via techniques such as injection molding or extrusion. For the study, a dog bone shaped mold was used. Next slide, please. So the results are encouraging. Additives were added per batch and varied by weight content, like 5%, 8%, 10%, and 15%, with a positive result as shown on the graph on the right screen. Okay, each dog bone specimen were subjected to a tensile test by using a UTM, or Universal Testing Machine, and according to ASTM D638, results were plotted and fitted with a 0.99 R² value. And with this data, we can also determine other mechanical properties like tensile modulus can also be found. So what's next for this project? Since this is only the first phase, other areas of interest would be, one, the study about mixing with other type of polymeric materials. This could be a major hurdle since different polymers are generally non-miscible or compatible with each other. This can lead to inferior mechanical properties. Number two, the study about the resilience from the process of repetitive recycling. Okay, this disadvantage of this process is represented by the existence of a limit on the number of cycles for each material. Three, to determine the other mechanical properties like thermal, flexural stresses, compression stresses, etc., etc. And lastly, most of all, put this on real applications. I would like to thank for this award, and thank you, RCE.
Thank you so much, Ramon, and it's great to see that you've got a process of innovation going, and it'll be exciting to hear what comes next. So,
thank you very much.